Hi everybody, welcome to our tutorial. Glad to have you back here. So in the last, I would not say the last, but we almost finished the class. And this tutorial is another extension to EMR, electromagnetic radiation. Let me write it down, electromagnetic radiation. And in this specific question, we're gonna take care of power lines. Okay, so if I have here some pole and another pole, right? And between them, I have power lines. And I want you to notice that how the subject that we just learned, electromagnetic radiation, can actually contribute to our understanding about power lines and about resistors and what we learned so far. So this is the idea of this tutorial. It doesn't matter which one you do first, this one or EMR, okay? So we actually gonna take care of power lines. So let me clean this one and write power lines. So in general, we have this string, this line with electricity, right? So I'm gonna tell you what's going on inside this one. So we have, actually, here is the power line. It's really long. And if it's really long, we can say it's a straight line in the Z direction. You can say it's a straight line because it's really, really long. And in this specific one, I don't know if you know it, but in the lines, we actually have alternating currents, which mean AC, alternating current, okay? Not DC, which is direct current, what you almost all the time do. There was a big battle between these two. And if you know the band AC/DC, the name is talking about that. People was wondering what to do. To deliver electricity to cities by alternating current, which means we're changing with time, or do a DC. Eventually, we decided to go with the AC for a lot of reasons. One of them is less danger than the DC. And the second one, less heat being absorbed by the environment, which means it's more economically smarter. You don't waste it. So our current is an AC current, AC, okay? And we have the signature I0, which this is the amplitude, the maximum value the current can get to. And it's oscillate. How we can do stuff that oscillate in math? Cosine, sinus. In this case, it's cosine, but it doesn't matter. And this is the frequency, the angular frequency, T. Okay, so this is the amplitude. This current is changing in direction, in the magnitude. It's really strong. Then it die out, and I go to the other one, reverse, right, the negative, and then back to zero. And how fast you do that? This parameter actually tell you how fast you're gonna do it. Okay, perfect. So we have a current, the changing in time, and we know actually that. Here, if I'm going to look at, let's zoom even more. So if I'm going to look at the cable, there's no difference at that point, at that point, at that point, that, whatever point that you like to look at, the properties of the materials are the same. It's rho. Remember, rho, the resistivity, perfect. And if rho is constant and everything is symmetrical, you can even say further the J, the current density is constant. It's also given, so that's what we know about this cable line. And what I want to ask you is, this is a power line. So what is actually the power that we have in the line? Okay, so let's write it down and go to the other board. So what is, first question, what is the power, which means watts? Remember, which this is a joule per second. How many joules this cable is actually throwing to the air, okay? Hitting the air. This is watts. What is the power, okay, of the power lines? Power lines. So let's dive into it. So what is the formula for power? P equal to? Yes, but before that, I would like to say this one. It's easy to remember. P equal to V. V, you know, like a check mark. That's how I want to think about it. But you are correct. We don't have anything about the voltage. So maybe it would be smarter to actually, I didn't tell you, but we know the diameter, the radius, sorry, of this one, which is A. But we know some properties and also geometry of the cable. So instead of talking about V, we can use Ohm's law, which is the V law, and extend this to that one. R multiplied by I squared. We can do that, right? And if you want a way to remember it, with the big power, come a huge current to the square responsibility, okay? Perfect. So we know that this is the power, so let's break it down. We know we know I, right? It was given. What is I? I is this AC current, right? So this is it. The amplitude getting squared, the cosines, omega t getting squared. Perfect. And this been multiplied by the resistance. What is the resistance of this cylinder? Remember the formula for the resistance? Is exactly, it's rho, the length, and A. Rho is given, is a constant, perfect. L is also given, it's the length of this wire, L, okay? I said it's the length of the wire, or just through the wire, I put L inside. And A is the area that the charge see when they're going through the cylinder, right? So it's also given. We know that the diameter, we know that the radius is actually A. So this one is actually pi A squared, right? That's what we have. So we end up with this term, rho L pi A squared multiplied by I0 squared cosines omega t squared. And I want you to think about that, keep that in mind, okay? It's gonna be really important later on. So let's move to the next question. The next question asks, okay, Ron, we find the power, but we know that if the charge, if the current is going in that direction, or the other way, you know, that direction, so what is the electric field that actually suck this charge, right? You suck this charge, right? Something is leaving this charge. This is the electric field. So what is the electric field? I'm going to that board. So what is the electric field inside this line? What this is big. What is the electric field inside the power line? The power line. Question? So I want to give you a new formula, okay? I don't know if we discussed it before, but it's really good. Remember Ohm's law? Remember it? We can break it down to a vector form. You see, this is all a scalar. You see, there's no direction here. There's V, which is the voltage, the energy I put in this part of the wire and in this part of the wire, right? I have the current, which also, it don't have a direction. You have minus sign or plus sign, but that doesn't say go up, go down, go to the left. There's no direction, okay? And also the voltage. You can say plus minus, and you can do minus plus, right? So it doesn't have any direction. They have a value. It's a scalar. Also the resistance. It's not a direction. You say go that way, go that way. Sorry, don't say that go that way. He said, I'm this material with this geometry, deal with me. That's why. But we already know each one of them to write them in a vector form. What do I mean? Remember what was V? V was the integral, right? V was the integral on the electric field, right? DL, right? That's what we had, right? And remember I was also a vector. Which one? The current density, right? dA. And L, who is R? Actually, we just wrote it below. So L, right A. This is R. And if I want to do it like kind of general, we can put here another integral, right? And say there's a lot of DL, right? Or a lot of dA, you know, just as a constant, okay? So this is the general case, a really general case. But what I can do, I can talk about not all the wire, only a piece of the wire. Which piece? Instead of talking of all the wire, right? I can take a small piece of the wire in the length of DL, right? With the area DA, and I just want to solve it for that one. So I'm not gonna sum them all. I have only one, this volume, right? So if I'm gonna take care only of this small, it's even a dV, it's a really small volume, only this one, I can actually neglect the integral. Agreed? Taking only one, I don't need to sum them all, only one. And then I said that E, the electric field, is going in that direction, right? Is this distance dl, but also the resistance needs some length. It's going away. dA here, the current meeting this dA, the current, the J, right? Is going through this area. But this is the same area the resistor is going. And then we get to another way to present Ohm's law, which is E, equal J, two vectors, and some constant, rho, the resistivity. So this one is called differential Ohm's law, okay? It's a more, instead of talking in general terms, this one is really specific, okay? It's with the vectors, and it's correct for every location in space. And at this point, I know that the electric field must be equal to J multiplied by rho, okay? You see this? It's correct to every point in space. Perfect. So why we did all this? Because we want to find the electric field. And Ohm's law is not working well for us because we don't know the voltage, okay? So let's go in, because not we don't want the voltage, we don't need the voltage. We want actually to get E, okay? So let's dive in. So let's use this formula. So E equal to J. As I told you before, the current is actually split equally between each part of the wire, right? The wire is symmetrical, it's a cylinder, right? So I can write J as I divided by A, right? I can do that. This is the density. What is the unit? It's ampere, right? Divided by area, meter squared. So this is whole, and I already know the resistivity was given as a constant. Perfect. So what is A? Pi A squared, right? And what is I? It's I0 cosine omega t. Perfect. And rho, zero resistivity. And this is the electric field. And if the current is going in that direction, in the Z direction, along the line, I can even add here the Z and say if this is the magnitude, this is the direction. Any questions? Okay. So if we have current that go in that direction, according to the right-hand rule, what I know that this wire is actually producing also around it, a magnetic field, right? So if we found the electric field, let's talk about the magnetic field that this wire is giving us. I'm going to the other board. So we already know that you have a magnetic field, and we can also state what is the direction, right? So what is the magnetic field, right? Which means we also want to know its magnitude, and we also want to know its direction, right? This is the two things. So how we can deal with the direction? We said, dude, look, you have the wire, got it. You have the current going that direction. So if you grab this wire, for example, if this is my wire, and I grab it, I can see that the thumb actually pointing at the eye, the direction of the current, and the finger is gonna curl in the direction of the magnetic field. So the magnetic field would be in the direction, right? The direction. That's what I'm expecting it to be. So we can already say that B is actually in the theta direction, right? And of course it's changing. If the current is going that way, right? It's the AC going that way, like this. You go that way, okay, no problem. It's going the other way around, okay? Important to notice it. Can you do more zoom to the board? I think there's a lot of, here's the waist area. Yes, perfect. Good. How we can find the magnitude? How we can find the magnitude of the magnetic field? Remind you, we have two options to find the magnetic field. On the one hand, we have Biot-Savart. Biot-Savart is the more complicated way to do it. If we have a crazy geometry and stuff not nice, some angles and stuff like that, go with Biot-Savart. This is probably the easy way to do this kind of things. But on the other hand, if we have a long stuff, infinite stuff, it can be infinite plane. It could be infinite wire, okay? We have some symmetry. We can play with the symmetry using Ampere's law. So in our case, okay, what is the best first guess would be Ampere's law, because in our case, the wire is really long, which means the diameter or the radius of the wire is really small and it's really long. So we have some infinite symmetry. Agreed? Perfect. So we're gonna write Ampere's law. So Ampere's law is saying taking the loop integral, the closed loop integral, closed loop, which we can by our mind do something, whatever we like, dot dl, whatever we like, and this must be equal to mu0 multiplied by I k. I'm gonna delete the angle stuff. Okay, not relevant here. To all the current that's going inside, right? This loop. Okay. So what would be a smart decision? It would be which loop we're gonna choose. We're gonna choose loops that actually gonna take care of this dot product. Gonna make it 0. Gonna make it pi over 2. You know, gonna make it 1, which means cosines would be pi. It would be 0, right, or 2 pi. And here it's the angle would be pi over 2 between B and DL, the angle. And also, if we know some specific angle was given, go ahead, play with it. But this would be a smart decision. Which loop should I imagine in my head? I-pen is all the current that penetrate the area that this loop is closing, right? If we're gonna take a rope and close it, oh, I have here some area, right? If it's penetrated, it's inside. So something that we didn't discuss yet, but when Maxwell wrote all the 4 equations, okay, of electromagnetism, he noticed that if we're gonna change the magnetic, remember this term? Remember Faraday law? If we're gonna change the magnetic, I'm gonna produce some electric field, right? And he said, gee, this doesn't make sense. How it's come that I'm changing the magnetic field and it produce some voltage in the electric field? But if I'm gonna change the electric field, I would not say changing magnetic field. So he understands that here there's a correction, okay? There's a missing part here. And this missing part is the constant of the electric field, okay? And here is the changing electric flux, okay? So this is Maxwell correction for Ampere's law. So every time you are writing Ampere's law, you need to notice if this is missing. And the reason this was missing is most of the time it's neglectable, okay? That's the reason it was missing until now in the class. But right now, I must telling you, this is the full way to write Ampere's law. Okay, this is the way you should do it. Okay, got it? Nice. So let's use Ampere's law in our case. Okay? So in our case, if I'm gonna have an infinite wire, and I know that the magnetic field is going that direction, in the tangential direction. So I want an easy life, right? I want a loop. That's the goal when you do Ampere. You need to find a loop. I want a loop that would actually fit perfectly with the direction of the magnetic field. Why? Because cosine of 0 is 1, right? So I'm gonna do a loop also like this. That's the loop I'm gonna do. Okay, I'm gonna do a loop around the wire. Okay? So what I actually told you is that I want to do this. I want the loop. I want to have the loop, which looking like this. Like this. B, I know it is in the direction of theta, and I know that it's gonna be dependent of the distance from this wire, right? Dot DL. Who is my DL? This, right? Which is R d theta in the theta direction, right? Tangentially. So this one is killed by each other, which means the cosines between them is 0. So the dot product is dying away. B, depending on R, but we're running on theta. So B can get out of the integral. So we have B as a function of R. And here we have an integral of R d theta, right? R also can go outside of the integral. And this one is a full cycle, which means 2 pi. So we're ending up with having on the left-hand side this term. B R 2 pi R. That's all, right? And this one must be equal to the left side, the right side, right? This is Ampere's law, this is what Ampere said. So let's deal with this. Okay, so this equal to, who are the current that actually penetrate this area? Who dare to do it? The wire. The wire trying to push current through this area, right? So I can already write this equal to mu 0 multiplied by the well-known I 0 cosine right omega t. Given, right? I know, perfect. But we didn't finish. We have the correction. What is the correction? I'm going to say, write this constant of what is the environment. This is the environment. Let's say we're in L, which in a good approximation, it's vacuum, right? So I don't need to change it. But what is the electric flux that we have? Which means not who is the current that actually poking this, who are the electric field that try to poke this? Who is the electric field that trying to penetrate it? That's the idea. And derivative it by time, okay? So in our case, the flux is pretty simple. Remember how you write flux? It's equal to the sum of small fluxes, right? And this one is equal to E dot dA. In our case, we found E. Remember previously, it was I0 cosine omega t, right? Rho 0 divided by pi a squared. And we know that if we're going to sum all the small dAs, the only one that matters is the one of the wire, because you don't have electric field that penetrate this one here, right? There's no electric field here. So dA is actually pi over A squared, so they're actually gonna cancel each other. So the flux phi E is actually equal to only this. Rho 0, I 0, cosine omega t. Yes, clear? And it's not enough. A flux does not make magnetic field. What do make a magnetic field? Changing flux in time. Do our current change in time? Of course, it's changing with time. It's a cosine, it's an alternate current. The current going that direction and then change direction, go that direction and then change direction, right? That's what it's doing. So we must write the derivative of that. So all the constant can live happily outside. What is the derivative of cosines? Minus sine. So here I'm going to put it minus, and here I'm going to write sinus omega t, and this omega also come here. Okay? Perfect. So this is the full term, but now I'm going to give you some approximation. Rho 0 multiplied by epsilon 0 multiplied by omega is a really small number when we talked about power lines. Really small. Okay? So in that case, that means that this term is actually dying out. Actually, you can say it was not that relevant to our case, but I wanted to emphasize something we did not discuss yet, which is that the flux of electric field can contribute to your Ampere law, okay? Usually in the exam, okay, I want you to think about that, okay? This most of the time, what you actually need. If somebody said infinite line, infinite plane, whatever it's infinite, probably you have a good symmetry. Good symmetry is good for Ampere's law, okay? But if you see the talking about changing stuff in time also, a flux of electric field, you said, oh shit, I need this term. Otherwise, I'm going to be fucked up and I'm going to write nonsense, okay? So most of the time, you don't see it in our class, but it can be on the exam, okay? So be aware that sometimes you actually need this one, okay? Perfect, okay. So we end up with this term, which was the left-right hand side, equal to mu 0, I 0 cosines omega t. Perfect. I just remind you that what we actually want is to find b. So we're going to divide the two of them. I'm going back to this board. So after doing what I like to say a massage to this sentence, you're going to get that b as a function of r is actually the permeability, which means how much the environment around is sensitive to a magnetic field, multiplied by the amplitude of the current, and the magnetic field, of course, is changing in time because the current which produces is changing in time. So you have this cosine term, and this is divided by 2 pi r, which means how far I am from the wire. It's a constant, right? How much I'm far away from the wire. Perfect. And this is the magnetic field. Yes. And in which direction the magnetic field is? Okay, wait a second. And I think I have a small mistake here. Wait. And yes, I was a little bit wrong when I said something. Okay, this is a really good example. I want you to follow on. Go to back to this board. Okay. What I did was perfectly right. Okay, but what I did was solving the equation when my loop is outside of the wire. You see? But I can actually zoom into the wire, right? I cannot look at this picture. I can look at this picture. This is the wire, right? This is the wire, and I did my loop here. Okay? So there's a lot of currents that go inside. There's I all over the place, right? Some of them I'm gonna catch. You see these two? They're gonna enter my area, this, but some of them, what? I'm gonna miss out. So our term is not fully developed for all space. We neglect what's happening inside a wire. How we can fix it? We need to fix this term. You see that I'm right here, all the currents that we have, right? But if we're gonna add some fraction, a correction factor, we can actually make this right for all space. What is this correction factor is? Okay, this one. What is the correction factor? I'm gonna take another this. So we need here to write, multiply by some fraction, something that's gonna correct it. So this one is actually gonna be pi. It's gonna be, okay, I'm gonna tell you the concept. What's actually making me catching more currents? If I'm gonna have a big loop, a big area of the loop, I'm gonna catch them all. If I'm gonna have a tiny loop, a lot of current would go by me, but I would not catch it. Only some of them are gonna catch it. So I want to write what I have divided by the whole thing. This would be a perfect correction, right? Let's write it down and then explain it again. So this correction factor is actually pi r squared. This is what I have. This is how much I have divided by the maximum, pi a squared. This is actually the ratio that's gonna let me know if I caught everything or not. Agreed? Any question about that? It was clear, this concept? When I was a student, it was not that clear to me, so that's the reason I asked him that.
Can I ask a question?
What?
Can I ask a question?
What?
When R is greater than A, is that ratio just 1?
When R is greater than A, so you actually, this should be 1, okay? So this fraction is right only when you're inside the wire. When you get to 100%, which means R equal to A, you actually got everything you have. When you go outside of the wire, your loop is so big, the area is included, all the currents in the wire. So I'm gonna clean this, and I want to go to this board and have 2 cases, okay? This is this is R. R is bigger than A, right? But if I'm inside the wire, I need this correction. And this correction, how it's going to contribute to me, it's going to be the same thing, right? It's going to be the same thing, but with the correction that I just wrote down, which is R squared divided by A squared.
Can you move the camera, please?
What?
The board. Camera, please.
I don't understand the question.
The camera. Could you just move the camera?
The camera. Follow me, camera. Okay. With my power of my will. Okay. So this term is actually what we did before. It's holding when my radius, the radius of interest that I'm actually looking at, is bigger than A. This is what we wrote before. It was perfect. The correction factor was actually 1. It was perfect. But if we are inside the wire, which means R is smaller than A, we need this correction factor. Here it is. This correction factor. The pi was divided. I don't need it. Okay. And I can see that this one cancels that one. And this behave differently. Look, this one is actually equal to 1, this R and this R. So we can put here A squared, and here we have only R. So this is like a constant, not really constant, it's changing in time, multiplied by some linear. See, that's what's going on outside. Sorry, that's what's going on inside, okay? Which means inside the magnetic field is actually accumulate more and more Tesla, more and more magnetic field, as you go to the other wall, but when you pass the limit of the wire, you're actually gonna die out in that fashion, 1 over R. Okay? In infinity, I would not notice any magnetic field. Close to the wire, you can see that this term is actually equal. When I put here A, right? This cancel out, here A, and they're the same. Okay? This is the magnetic field. In which direction? All the time and then theta direction, right? And of course, also can change sign depending on the cosines. So we found the magnetic field. Good question. Wonderful question. Like it. Okay? Let's go to the next question. I'm going to clean this board, back to this board. And my question to you is, what is the vector, the pointing vector? Okay? And the one that already saw the EMR, the EMR question, and the EMR question that you have on YouTube, already know what I'm talking about. And the one that don't worry, we're gonna do it together. So my question to you is, what is this vector, which its name is the pointing vector. And I want you to notice a really common mistake. Pointing is the name of somebody, okay? It's not a pointing vector at someone, okay? It's the name of the guy. And pointing vector, it's a really interesting unit. It's, the units of it is power divided by area, okay? Which I can say, how much joule do I throw per second through on this area, which means if I have this long wire, okay, this long wire, before it was just throwing joules, you know, this is joule, okay, throw it away, joule 1 second, 2 seconds, 3 seconds, but right now, I also need to take care of how much area that I have to throw joule through it, right? Okay, for example, you can think about that lamp that we have here, this lamp, actually contributes 100 watts, which means joule per second. That's how much it's throwing to there. Every second, let's say joule per second. Every second, 100 joules, 100 joules, 100 joules. And the lamp, when you touch it, it's really hot, right? This is a lot. But you want to know a crazy fact? Humans also produce 100 watts, which means right now, my body temperature is 36.6 degrees. I'm throwing to the air 100 joules, like the lamp. Why I'm not so hot as the lamp? The answer is this term. We have a different area, right? The lamp is so small, it's a really small area. So when you touch it, you touch almost all the joule that this one can produce. But humans have a huge area surface around my hand, my here, my back, my everything, the leg, everything. It's an area, right? So that's the reason this was evenly distributed. So this term, the pointing vector, is actually a smarter way to talk about dissipate of energy. Okay, you understand the concept? So what is the formula of electric magnetic dissipation of energy? Okay, what is the pointing vector? So the formula is going like this. It's this vector, S, and it's equal to the cross between electric field and magnetic field divided by mu0. Okay? This is the formula, really important formula for the exam. Okay? And it's going to be answered again. What is the pointing vector? You know, okay, to find the pointing vector, I need to find E, I need to find B, do the cross, divided by the constant, I'm done, give me my 100. Okay? That's how it's being done. It's really easy, okay? So we already did the hard work. Remember? We found E. What was E? Okay? Let me write it down for you. E was I divided by pi a squared multiplied by rho, right? If you remember, this was J rho. We made a new term, which called the differential Ohm's law, and we said it's the current density multiplied by the resistivity. That's it. And in what direction? It was along the line, pushing the charge, Z. So this is Z cross B. We just found B. And I want to take care of the dissipation of energy through the surface area of the wire to the environment. I don't care about, this radius, dissipate energy to that radius, dissipate energy to that radius. No, I want to know the outer shell of the wire dissipating to the air, okay? So this one is actually, which means this is the magnetic field in the special case of R equal A. That's what I said for the magnetic field. So here it is mu 0 I 0 cosine omega t, right? Divided by 2 pi A. That's what I said. And in which direction? Theta direction, right? So let's deal with I. All of these divided by what? Mu 0, right? So first of all, mu 0 is dying out. Don't need you. Pi, okay, everything is okay. What is the cross between Z and theta? You remember it? It's theta Z. And I ask what is Z theta, which means I'm going the wrong direction, which means I am out, but I need to correct it with the minus. Minus our direction, okay? Perfect. So this is minus R, good. And here, you see that actually we have all the term of the current being squared. You see it? This is I, remember? This was our I, right? So we can say I squared, right? 2 pi A, let's write it. So we have 2 pi squared, A to the 4, you see A squared and A here. Sorry, not to the 4, to the 3, I think, right? This is a mistake. Mistake, right? And good. No, I said squared. Here, I think it's to the 3rd, right? Sure. To the 3rd. From here to the 3rd. Okay. Weird. Okay, I'm gonna see if I have here a mistake. Minus R, I squared, we have this law, right? Resistivity, and we have, and that's it, right? I tell you what I did. Here, I put the general case. If I'm gonna do not A, but I'm gonna put R, right? I think that's what I did here. I put here R, so I can, let's put A. It's okay. Let's do it like this. It's okay. Okay, this is what we had, right? So I'm cleaning this one. No, I'm cleaning this one. So if we actually want to find what is the watts, what is the power that we have, how we can connect this one to power. The only difference is the area, right? Back to this board, Okay, so if I want to connect the pointing vector to the watts, I just need to fix the area thing, right? So let's go back here. So if I want to find P, so what is the power of the wire, what I actually need to do, I can find it using S, right? I can say that P is equal to the magnitude of S, right? Because P is not a vector, S, multiplied by A. What is my A? What is the area of the wire? It's L, right? Multiplied by this one, right? Which is this area is a squared pi, right? So I can write here pi a squared, right? And here I can write the Poynting vector I squared rho 2 pi squared a to the third, right? So pi and pi going out, this dot with that, and we have that p is equal to I squared rho and L. We have that L, I squared rho L, pi, right? Pi A, and this is 2, this is, I think it actually, I need to check, I think I have a mistake over there, but this, I think we should have here to the 4, I want to check it, but here it should be on the 4, I want to check it, okay, count in, okay, and what we actually have here,
that A is another section.
what? A is this, it's all around it, okay? Ah, sorry. Now I got you. This is 2 pi. Okay, gotcha. You mean this is 2 pi A. Sorry. So this is 2 pi A, right? The one around it. So, okay, now it's making sense. Okay, so this is A to the third. It cancels with this. Is happening to be A to the 2. This 2 is cancelled with this one. Right? So we have here pi. And what is this term? This is R, the resistance. So we have I squared R. This is familiar to you? So we actually got back to the point we start this exercise. That's what I want to show you. Okay? So the energy that's being sent into the environment is actually the power, and you can see it by the cross between the electric and the magnetic field. So guys, this was an extra really good question from the tutorial. I really want you to see the electromagnetic radiation tutorial that we have on YouTube. The one on YouTube, it's really important. Please see it. If you have a question, right below. Thanks you very much. Next week is our last meeting before the end of the semester, right? And good luck, guys. If you have any question, you can go ahead and ask me, but we finished the question that I had in mind for today.
Thanks, Ron.
Thanks, Ron.
Thanks, guys. Thanks for showing up.
Cheers.